Well, hello, math students. It is Sunday. It is July 10th, and I welcome you to our live stream this Sunday night. Tonight, we're going to be talking about logs and exponentials. And this is really part of a series of live streams that I'm doing for AP Calc students this fall who are just getting ready to take that class. And there's some topics that I wanted to go over that will certainly help you as you get ready to take your AP Calc AB. And one of them that I have found that's very important to review is the idea of logs and exponentials. So tonight, what I want to do is I want to cover four things about logs and exponentials. So the first thing is we're going to talk about exponential and log function graphs and emphasize the fact that these are inverse functions. And we're going to show that graphically, and we'll talk a little bit about functions. Not going to dwell on that too much. Secondly, then I want to talk about how to use logs and exponentials when you're solving equations. Now, this will vary maybe a little bit different from how you were taught logarithms and exponentials and how to solve log and exponential equations. Some teachers teach it one way, some teach it another way. I'm going to teach you a way that I think that makes the most sense and is going to really help you when you get into Calc AB. Third thing I want to do is talk about the rules of logs and the rules of exponents, because you're going to need to know those, right? You're going to be using those definitely over and over again in Calc AB. And then fourthly, we're going to do some equation solving using logs and exponentials. And at the very end, I'll also do an application or two of exponential functions. Now, if you want to stay up to date with what I'm doing on this channel, be sure to subscribe to my channel. And you can also hit the notification bell so that you know when I push out new content. I will be pushing out new content throughout the year. And so definitely subscribe if you want to know when new content comes out. All right, so let's get right to it. I want to start off by taking a look at exponential and log functions and emphasize the fact that they are inverse functions of each other. So if we consider these two functions, f of x and g of x, log base 10 of x and g of x being 10 as a base raised to the x power, those are definitely exponential functions, or excuse me, inverse functions. And I'm going to go into Desmos and show you the graphs of these functions and just remind ourselves what they do look like. So let me share that. Okay, let's see if we can bring this up. And we will go over to, here we go. Let's share this back. All right, so you can see here that I have graphed in Desmos log of x and 10 raised to the x power. And there they are. So that should not be a surprise to you. So this is an exponential growth function, 10 raised to the power x, while this is a log base 10 to the power x. And they're inverse functions of each other. We can determine that graphically or confirm that by graphing the line y equals x, because when we do graph that line, you see that they are mirror images of each other. They are reflections across the line y equals x. That's one characteristic of functions that happen to be inverse functions, is that symmetry across the line y equals x. So these certainly are inverse functions. And let me go back to, let us go back here. And I want to talk about the domain and the range of these functions, right? Because one thing that you want to remember is what are the domain range intercepts of x and y intercepts of log and exponential functions, and how they end up being transformed when we change the equations of the function. So if we go back to Desmos, and there we go. So back into Desmos, and we take a look at the exponential function, right? So we can see when we're looking at this function here, that the domain is all real numbers, right? So our domain is negative infinity to infinity because it does stretch from negative infinity back this way. And the x's continue to go towards positive infinity. The range is another matter, though, because in this function here, 10 raised to the power of x, the range really goes from 0 to infinity. And that's exclusive because we have a horizontal asymptote at y equals 0. And so that's our domain and range. And you can see that there is a y-intercept at 1, 0. So I have an intercept at 0, 1, I should say. So that's the intercept there for 10 raised to the power x. Now let's contrast that with the logarithm function. And this is log base 10 of x. But notice that over here, the domain now, since they are inverse functions, the domain of this function is going to become the range of its inverse. So the domain here is 0 exclusive to infinity. There happens to be not a horizontal asymptote, but now a vertical asymptote at x equals 0. So my domain stretches from 0 exclusive out to infinity. But my range now becomes what was the domain of its inverse. So the range is negative infinity to infinity. And the intercept, instead of being 0, 1, is now an x-intercept at 1, 0 for an intercept. I want to remind you about transforming functions, right? So we can transform any of these functions by doing vertical shifts, horizontal shifts. We can reflect across the x or the y axis. And so you need to be aware of that. For example, let's fool around a little bit with these functions. I'm going to get rid of my annotations there. And let's do a vertical shift here. So if I take log base 10 of x and I put a +1 there, what I've done is I have just shifted that up 1 unit. I didn't alter the vertical asymptote. It stayed put, but now it was just shifted up vertically by 1. I can do the same to the exponential growth function by adding 1, and it then shifted up by 1 unit, and the horizontal asymptote is now at y equals 1. So we can do vertical shifts up and down. We can also do horizontal shifts, right? And that is accomplished by changing the x value. If I put an x +1, that is a left shift by 1. So you can see that this logarithm function just shifted over, and that vertical asymptote went from x equals 0 back to x equals -1. We can also do the same here by putting a +1 into the exponent up here. See if we can accomplish that. And put a +1. There you go. And so that, again, was a left shift. Didn't alter the horizontal asymptote any, because a horizontal shift won't change any horizontal asymptotes. But the point that was at 0, 1 has now moved over and is -1, 1. So just review how to transform functions and all of those rules of transformation of functions: vertical shifts, horizontal shifts, vertical stretch, horizontal stretch, reflections across the x and y axis. They all apply to these two functions. All right, so let's return back to our notes here. And what I want to do now is kind of move on to our second thing that I wanted to cover, and that is we want to use the fact that these are inverse functions of each other to help us solve equations. And we're familiar with using inverse operations to solve equations in algebra generally. I want to just review some really basic things that I know that if you're getting ready to go into AP Calc, you already know. But I'm talking about inverse operations to solve equations. For example, if I am doing this equation, 5x plus 10 equals 48, and I'm trying to solve it for x, I'm going to reverse the operations that have been done to the x. This is a plus 10, so I'm going to reverse that, right? The inverse operation of addition is subtraction. So I then subtract 10 on both sides, giving me 5x. 48 minus 10 is 38. I now have 5 times x. I want to solve for x by reversing that, or using the inverse operation of multiplication, which is division. So I divide that by 5 on both sides, and I get x equals 38 fifths. Now, if you're watching this and you're wondering, gee, why are you showing me so much basic algebra here? I mean, this is Algebra 1 stuff, even maybe prior to Algebra 1. I'm just making a point here about inverse operations, and then I'm going to move this into inverse functions and how they help us to solve equations. So that's an example there. Let's move it up a bit and talk about exponents and inverse operations of an exponent. Here I have an equation, x squared minus 28 equals 0. I want to solve this for x, so I'm going to first add 28 to both sides. Okay. Now, I want to isolate the x, so I need to consider what is the inverse operation of a square. And the inverse operation of a square would be a square root. So I'm thinking about the inverse operation of squaring as being square rooting. And the square root of x squared is an x, and this is plus or minus the square root of 28. All right, I can simplify this radical 28 as 2 root 7, but that's not the point here. It's that I used an inverse operation. I can do the same thing here. I've got a cube root of my variable x, but I'm going to first start off by getting rid of my plus 11 by an inverse operation of subtraction, giving me 2 cube root of x is equal to 14. I will then reverse the operation of multiplication here by dividing by 2 on both sides. That's going to give me the cube root of x is equal to 7. All right, and now the inverse operation would be to raise to a power 3 on both sides. And the act of cubing a cube root, they reverse each other, and this leaves me with a solution of x equals 7 to the third power. Now I want to move on, though, students, to inverse functions, right? How to use inverse functions. I just did inverse operations, addition, subtraction, multiplication, division, and roots and powers being inverses of each other. But now let's talk about inverse functions. And let's do that kind of in the context of trigonometry. So back in pre-calculus, and just kind of backtracking a bit here, right? I'm not assuming that you have I'm assuming that you have been exposed to exponentials and logarithms before. So I'm not trying to teach things from scratch here. I'm just kind of going to do in this session a very quick review of logs and exponentials, and show you what you need to know to be successful in Calc AB when it comes to those two functions. And so I'm assuming that if you're watching this, that you've probably taken pre-calculus, and one of the things you had to do in pre-calculus is you had to solve trig equations. And I want to show you how we used inverse functions to solve trig equations. And here we've got an equation that we want to solve over the given interval of 0 to 2 pi. And that is sine of 2u plus 4 cosine u equals 3 cosine u. Well, the first thing that we notice here is that we do have separate arguments here. I have a 2u and a u and a u. And so I want to definitely use a trig identity that would allow me to convert that 2u argument into a u. So I'm going to use a double angle identity. This is one that you should have committed to memory. That could come up in Calc AB. But sine 2u can be converted into 2 sine u cosine u. Okay, that's one of the trig identities from precalc. And then I've got plus 4 cosine u equals 3 cosine u. Well, I do notice that I could bring this 3 cosine u over to the other side and combine it with the 4 cosine u, and I'm going to do that. That's going to give me 2 sine u times cosine u plus cosine u equals 0. Right? So right there, I just did an inverse operation, right? I subtracted 3 cosine u on both sides to get rid of this 3 cosine u. Now, the technique that I'm going to use here is factoring. I recognize that I do have a greatest common factor between these two terms on the left-hand side. So I'm going to factor out a cosine u, leaving me inside the parentheses 2 sine u plus 1 equals 0. And we're going to use our zero product property to solve this from the rest of the way, because the zero product property says that if I have two things that are multiplied together, and the two things are these two factors, and their product is 0, it means that at least one of them has to be equal to 0. So we split this up and say, well, cosine u has to be 0, or 2 sine u plus 1 has to be equal to 0. And then we solve those two equations independently to find our solutions to this equation. Now, how do we do that, right? I'm trying to find what u is equal to, but it's captured inside of a cosine right here. So what I'm going to do is I'm going to use an inverse function. And the inverse of cosine is, no surprise, what we called inverse cosine or arc cosine. And so the function, or I should say the operation that we're going to do on both sides is what we would call the arc cosine. I'm going to take that on both sides. So this is basically what I'm going to do. I'm going to take the arc cosine of both sides. And this would be, of course, cosine u, and this is 0. So this is the operation that I am doing on both sides, taking the arc cosine. Well, the arc cosine, or the inverse cosine of cosine, is just u, right? These two, in a sense, cancel each other out, and it leaves me with u. And my solution is u equals the inverse cosine of 0, which is to say, in the unit circle, what are the u values where cosine is equal to 0? And cosine is equal to 0, if you know your unit circle, at pi over 2 and 3 pi over 2. So those are two of our solutions. All right, so my point in the context of logs and exponentials, which is the topic of this video, is that I just used an inverse operation, because cosine and arc cosine are inverse functions of each other, just like exponentials and logs are inverses. Over here, similarly, I'm going to be solving this for sine u. Now, before I take the arc sine on both sides, I do need to isolate the sine and get it by itself. So I'm going to subtract 1 and divide by 2. So I have sine u is equal to a negative 1/2. And I'm going to then take the arc sine on both sides. So I'll do it this way. I'm going to say, take the arc sine of that, and I'm going to take the arc sine on that side. The arc sine of u is just u. They, in a sense, quote unquote, cancel each other out. And my u, in solving this part of my solution here, is the arc sine of a negative 1/2. So then these solutions here are going to be found by determining, well, where on my unit circle is my sine function a negative 1/2. And this should be in the third quadrant at 7 pi over 6, and over in the fourth quadrant at 11 pi over 6. And so my solutions here as my final answer are the combination of these two problems that I solved. When I set these two factors equal to 0, I can state that my solution here is pi over 2, 3 pi over 2, 7 pi over 6, and 11 pi over 6. That's my solution set to that problem. And again, I'm showing this to you just to demonstrate the idea that we like to find solutions when our variable is inside of a function, is an argument inside of a function, is to release it, to get it out of there, I have to use an inverse function to do that. And that came in handy when solving trig equations. Now, let's move on to the next idea that I wanted to cover tonight, and that is this idea that since logs and exponentials are inverse operations, we're going to use them to solve equations. Now, this is where things maybe vary a little bit from how you were taught in your Algebra 2 class or your pre-calc class. A lot of teachers would teach a solution to this particular problem by converting it from a log to an exponential function. And I'm not really even going to address that tonight. I'm not going to address how it is the mechanics of saying, here's a log function, convert it to an exponential. I'm not interested in that. I want to consider inverse functions. For example, if I am faced with this equation and my objective is to solve it for x, I want to get rid of the log base 2. Okay, every logarithm has a base. If there is no base and it's just log, it's an assumed base 10. This is a log base 2. So what I'm going to do is I am going to do something that's called exponentiate. That's not a word. It's not a word that I hear often used in Algebra 2 classes, okay? But exponentiate means I am going to raise power on both sides. That's an algebra move. I'm doing it to both sides of the equation. I am going to raise 2 power on both sides. Now, when I do that, I've got 2 raised to the log base 2 of 3x minus 4. These guys cancel each other out, and it leaves me just the argument of the logarithm. So now what I have is I have 3x minus 4 is equal to 2 to the 7th power. And now I can proceed to solve this like I would. Now, 2 to the 7th, I believe, is 128, if I am not mistaken. 32, 64, 128, it is. So 3x minus 4 equals 128. And now I will add 4 on both sides, and then I will divide by 3. And I have my solution. So exponentiate is how I would get rid of a logarithm, because logs and exponentials are inverses of each other. 2 raised to the log base 2 are kind of reversing each other and canceling each other out. All right, that's how we get rid, or how I would solve a log equation here and get rid of the log to release the variable x from the logarithm. Let's take a look at another example. Here is a natural log. Now, ln is just a shorthand for log base e. Right, so this is log base e of 2a equals 9. And we obviously here, our objective here is to solve for the variable a. Well, in order for me to get rid of the logarithm, I am going to exponentiate. What base am I going to use for my exponentiation? It's going to be a base e, because I want to match the base of this logarithm. So I'm going to exponentiate with e as my base. Well, e raised to the log base e of 2a is just 2a. And 2a is equal to e to the 9th. Therefore, a is equal to e to the 9th over 2. And that is my answer. That's my exact answer. If I wanted to use a calculator, I could go ahead and get an approximation, but I am not going to bother. That's not the point of the exercise. That is my exact solution. E to the 9th divided by 2. Let's try another one. Here is log base 6 of w plus 7 minus 5 equals a negative 3. Now, so what I'm going to do in this case is I do need to isolate the logarithm before I exponentiate. So I am going to add 5 on both sides. So that's going to give me log base 6 of w plus 7 is equal to 2. Going to exponentiate on both sides by raising 6 power. This is going to release the w plus 7, and 6 squared is 36, and w is going to be 36 minus 7, or 29. That's my solution. Now, let's talk about how we would do this with exponential functions, right? So an exponential function is one where my variable is in the exponent, and that's certainly what we have here, 3 to the x equals 80. Now, a couple of ways that you may have learned how to do this in your Algebra 2 class, but what I'm going to do is I'm going to use logarithms. If I'm dealing with an exponential function and I need to release my variable from the exponent, I'm going to use logs on both sides, and I'm going to use a log base that matches the base of my exponential. So I'm going to take the log base 3 on both sides. That's the algebra move. The algebra move here is to say, well, let's take the log base 3 on both sides. So I'm going to take the log base 3 of 3 to the x. And I'm going to take log base 3 of 80. Now, what happens when I have log base 3 of 3 to the x, these guys cancel each other out. And it leaves me, or it releases that x from the exponent, and I just have an x over here. And my answer is log base 3 of 80. That is the answer. Now, if I wanted to get an estimate of that answer, and I have a TI-84, I'll show you one trick here. I definitely can do this on my TI-84. In your math command, if you go into math and scroll up, because this function is near the bottom, second from the bottom of this menu, log base. If you execute that, you can see that you can put in a base and then put in the argument. In this case, it was an 80. And we get our approximation, which would be out to 3 decimals, 3.89. So this would be approximately 3.89. Now, I haven't covered yet the rules of exponents, or I should say the rules of logarithms, that I do want to cover in this session. So, but I'm going to go ahead and show you what that is. Right? If you don't have a TI-84 that does an arbitrary logarithm like this, if you want to convert the base of your logarithm, and we want to say convert it to a base 10, what I can do is say, well, log base 3 of 80 would be log base 10 of the argument 80, and then I would divide that by log base 10 of the old base 3. Like that. So if you have a calculator other than the TI-84, you could then execute that, and you'll get the same approximation here, 3.89. That's what we call the change of base formula. And I'll mention that again here in just a few minutes. All right, let's try another one. This is 5 raised to the x plus 1 power. And we need to solve this for x. So I am going to use logarithms to do this. So I'm going to take log base 5 on both sides. I'll take log base 5 of 5 raised to the x plus 1. And that would be equal to log base 5 of 18. Log base 5 of 5 to the x plus 1 is just x plus 1. And over here, I have log base 5 of 18. And finally, to solve this one for x, I would just subtract 1 on both sides. and I get log base 5 of 18 minus 1. Okay. And if I wanted to get an estimate on that, I definitely could. But I'll leave that for you. All right, let's go down. Let's try another one. So this is e to the 3x power. And I'm going to, again, use logs on both sides. But before I do that, I do want to isolate my exponential portion of this. So I'm going to subtract 25 on both sides. So I've got e to the 3x equals 108 minus 25. And what's that going to be? I believe that's 83, if I did that right. Would that be right? I think it is. 83 plus 20 plus 108. Yeah. So I've got e to the 3x equals 83. Now, what I have to use is log base e, which is a natural log. So I take the natural log on both sides. In fact, once you understand this idea of using inverse operations, you just simply move straight to 3x equals the natural log of 83, right? You don't really have to say, I'm going to take the natural log on both sides. Just 3 to the x is natural log of 83. Therefore, x is going to be equal to the natural log of 83, whatever that number is, divided by 3. That's an exact answer, and we'll leave it at that. Now, let me mention the rules of logs and exponentials. Again, this session really is geared towards students who have completed precalc, getting ready for Calc AB. So these are things really that we shouldn't have to review. Most students have used these enough. During your pre-calc that it's kind of ingrained in you. But I'll mention a few of these here. I'll show you a few things that do trip students up in AP Calc that they need to brush up on. So here's your product rule of exponents. If you're multiplying like bases, you add the exponents. If you raise powers to another power, you are going to multiply the exponents here. If you're dividing like bases, you subtract the exponents. The zero exponent rule, believe it or not, I have quite a few students who forget this is something, right? Anything raised to the 0 power other than 0, which would be undefined, 0 to the 0 would be undefined. But anything raised to the 0 power would be equal to 1. It doesn't matter if it is a variable or if it is a number. The answer is 1. Also, if I have, this is our product to power rule. If I have two things multiplied raised to a power, then that exponent gets applied to both of those factors inside the parentheses. That also holds for quotients right here. And let's talk about the negative exponent rule. I just always encounter students at all levels of Algebra 2, Pre-Calc, Calc AB that just kind of forget about the negative exponent rule. And really, there's a couple of different ways that you need to remember the negative exponent rule. Here's one of them, right? If you've got a b raised to a negative power, and you consider that as being over 1, you're moving that down into the denominator, leaving behind the 1 factor that's already there, and the exponent will change signs. Some of your teachers probably told you the little jingle, go through the line, change the sign. Well, that's true. If you take something through the fraction line, you change the sign as long as it is a factor of the numerator or denominator. If you're moving it from top to bottom, it needs to be a factor of the numerator. And same if it's going from bottom to top, it must be a factor in order for you to be able to move it through the line. Can't move terms, obviously. Okay, so that's how you convert a negative exponent that's a factor. That's how you convert it to a positive exponent. Another way, really, it's the same idea, but another way that the negative exponent rule comes into play is when you already have a quotient that's raised to a negative exponent. You can convert the exponent to a positive exponent by just simply reciprocating the entire expression, the entire quotient. But again, that's, well, I'll just leave it at that. So that's just another way. Just be aware, be able to use that negative exponent rule as you're simplifying. One thing is for sure, you're never going to see a multiple choice answer on an AP Calc that has negative exponents. I could probably find one and make a liar out of myself, but I can't think of any time that I would see a multiple choice question where negative exponents have not been converted into positive using the negative exponent rule. It's also, you're really going to be, this isn't really part of this particular session, but you definitely need to know how to convert between rational exponents and radicals. So this is the idea here. We use that a whole lot. So you need to be able to be very comfortable with simplifying radicals and also converting between rational exponents and radical form. Okay. Now let's go down. Let's go down to the next section, which are laws of logarithms. Sorry for the graininess here on this figure, but this is something that is less used, right? These laws are less used than the rules of exponents. So I want to review these. Since you're going to be using logarithm functions in AP Calc, you got to know these cold. You got to have these down and know how to use them. I'm going to show you some examples of problems where I use these rules in solving log equations. But when, excuse me, when I have addition or subtraction of logarithms and my logs are to the same base log, if it's addition of two logs, I can combine them, or what we call condense them, into a singular log through multiplication. So addition between logs is condensed into a singular log through multiplication. And as you might imagine, if that's true, then it would also be true that if I'm subtracting like logs with the same base, that I would then divide, condense them through division, right? And so these are very similar, and these come from, and we could prove these through an application of the rules of exponents, but I'm not going to bother with that. You just simply need to know these rules, okay? Need to know them and know how to use them and when to use them. This third one here is called the power rule. And the power rule says that if you're taking the log, boy, that is really grainy. This is log base A of m to the n power, okay, is what that is. This is m to the n power of the log base A. What you can do through this power rule is take that exponent and move it to the outside and make it a coefficient or a multiplier in front of the logarithm. Okay, so instead of log base A of m to the n, it becomes n times log base A of just m. Very powerful property when it comes to solving equations and manipulating logarithm equations. Okay, now this right here, log base A of 1 is equal to 0, right? So anytime that you take the log of 1, you are going to get an answer of 0. Anytime that you have a match right here between the base of the log and the argument of the log, right? Log base A of A is equal to 1. Now, that, if you consider that that exponent is a 1 right there, that's why that's a 1, right? But because log base A of A, they are canceling each other out, leaving you the exponent. Okay, I could also write this rule to look like this. Log base A of A to the m is equal to m, like that. Okay, and here, this is another way. Right? This is kind of the looking at it from an exponential standpoint. This is A raised to the log base A of x is equal to x. And I just showed you in a couple of examples where I was solving log equations. When I exponentiate, these cancel each other out and they release the argument of that logarithm. And that's why that's equal to x. All right, and then number 7 here, this is what I showed you in the one example where I changed the base. This is called the change of base formula, which is very, very helpful when we're trying to maybe approximate a logarithm and our calculator only does log base 10 or log base e. So this is it. So whatever the new base is that you want to use, you're going to put the argument of the old log on top and the old base log as the argument down in the denominator. All right, now let's go. This is the 4th thing, right? More equation solving using logs and exponentials. So I'm going to maybe try to put some of these things together here that we've learned tonight into some more interesting equations to solve. So here is an equation to be solved. We're solving for v. And my strategy here is I'm going to condense this into a singular log. And then what I'm going to do is I'm going to exponentiate on both sides. So the first thing that I'm going to do is, since I've got addition of these same logs, I'm going to condense the logarithms into a single log. 2v plus 3 times 2v minus 3 equal to 2. So it's log base 4 of the product of these two binomials. What I'm going to do now is get rid of the logarithm. I'm going to do that by exponentiating. So I'm going to raise 4 power on both sides. Well, 4 raised to the log base 4 of that product of two binomials is just the product of the two binomials. So this would be 2v plus 3 times 2v minus 3 is equal to 16. So now I've gotten rid of the logarithms, and now it's just a basic algebra problem. I'm going to go ahead and solve this by multiplying this out. These are two conjugates, so I know that this is going to be 4v squared minus 9 is equal to 16. I can use the square root property to solve this. I don't have a v term in this quadratic, so what I can do is add 9 to both sides and get 4v squared is equal to 25. I can get v squared is equal to 25 fourths, and then square root both sides, and I'm going to get v is equal to a positive 5 halves and a negative 5 halves. Now, when we solve logarithm equations, right, we want to take our answers and be sure that that they are actually solutions. Remember that when we talk about logarithms, logarithms only exist when your arguments are positive. Remember what a logarithm function looks like. A logarithm function has a domain from 0 to infinity. So I can't take logs of negative numbers. So any solution that I come up with that would give me a negative value in one or both of my logarithms would be one that I would have to reject. I would consider it an extraneous solution. So when I put 5 halves, let's try 5 halves here. That's not going to be a problem with this logarithm. When I put 5 halves in here, 2 times 5 halves is 5, 5 minus 3 is 2, no problem. I like 5 halves, but negative 5 halves is going to give me a negative argument right here. That'll give me a negative argument, and so therefore I have to reject that as a solution, and my only solution here is 5 halves. All right, let's continue. You might imagine we're going to condense this, right? I do have the same bases here, log base 2. I am going to condense this using my properties of logarithms. Log base 2 of n minus 3 times n plus 1 is equal to 5. I'm going to exponentiate. I want to get rid of the logarithm, so I'm going to raise 2 power on both sides. These guys, boom, gone. I now have n minus 3 times n plus 1 is equal to 2 to the 5th power. And that would be 32. You didn't see me count on my fingers right there. So yeah, so 2 to the 5th is 32. Well, to solve that, I'm going to have to expand the product of those two binomials. So that's going to give me n squared minus 2n minus 3 equals 32. Sure hope this works out. I think it will. I'm going to subtract 32 on both sides to give me a minus 35. I'm going to solve this through factoring. That looks like n minus 7 n plus 5. Using the zero product rule, setting both of those equal to 0. N equals 7. N equals negative 5. But again, we need to go back and check these solutions to make sure they don't cause a problem in the arguments of our original logarithms. 7's not a problem, right? This would be log base 2 of 4 plus log base 2 of 8 equals 5. So both of my arguments would be positive. When I put it in negative 5, not going to work. That's going to make both of those logarithms have a negative argument. We reject that as extraneous. We're going with n equals 7. Let's see what else we got. All right, this looks like a beauty. I'm going to use, so this is an exponential function or an exponential equation. So that means I'm going to be using logarithms to release my variable from the exponent. So I'm going to have to get rid of the 9 first with this negative 9. So I'm going to add 9 on both sides. I'm going to show all of my steps here. So that's 2/3 times 5 to the m minus 8 equals 30. After I add 9 on both sides, I'm now going to multiply by that the reciprocal of that coefficient 2/3. I will multiply both sides here by 3/2. Right? Because before I take the log on both sides to get rid of the exponent, I need to isolate the exponential portion. I need to isolate the 5 raised to the m minus 8. So this is going to be 5 raised to the m minus 8. 2 goes into 30 15 times. 15 times 3 is 45. Now, a couple of ways that we could go here. In your Algebra 2 class, your teacher may have said, let's use log base 10. I'm going to use log base 5. So I'm going to take, my algebra move here is to take log base 5 of both sides. So log base 5 of 5 raised to the m minus 8 is just my m minus 8. And then over here, this is log base 5 of 45 and add 8 to both sides. And that's my answer. Now, the argument here is not 45 plus 8. It is just 45. If I wanted to convert this into base 10, just to show you here, right, that using the change of base formula, this would be log of 45 over log of 5. Remember, without a base on my log, I am inferring that it is log base 10. And then this would be a plus 8. Okay, so this on any standard scientific calculator, you could come up with that right there, that approximation, add it to 8, and you have your approximation for the variable m. Okay. Let's go and see what we have next. All right, so this is really going to be our last problem here. So we're going to get this in just under 1 hour. That's awesome. So here we go. Now, before I do this one last problem, which is going to be an exponential problem, I want to remind you that this week on Thursday night, I am going to be doing another live stream, and I'm going to be working a complete ACT math practice test. That's because we have an ACT test coming up this Saturday, July 16th. And so for my students that I've been helping on the get ready for this ACT, I'm going to do that live practice test. And I did this before I think it was the June test. And the way that I did it is I worked it just as though I was working it on pencil and paper if I was in a test situation. But I thought out loud. So I was thinking out loud as I was processing the problems. And then after I did 10 problems, I would then go back and grade it during the live stream. And then if there were any problems there that I thought were worth maybe mentioning, kind of the method that I used, or maybe some alternative methods that you could have used on a problem, I went back and addressed those before I continued on with the next 10 problems. And of course, if you join live, then you'd be able to ask questions as well, and I'll be able to check out questions in the chat if you want to join that live. Or if you don't do it live, then you could watch it. You could watch it Friday before the test on Saturday, and that is going to be Thursday at 8 o'clock. So that'll be this Thursday, July 14th at 8 p.m. Eastern Time. So here's our last problem. And also, don't forget, class, if you want to stay up with what I'm posting here on YouTube at my YouTube channel, which includes my live streams, then please subscribe to the channel and turn on the notifications so you get notified when I schedule a live stream or post a new video. So here's the last problem. A new stock entered the stock market in January 2012 at 72 cents per share. 4 years later, the price per share was $3.85. Using a continuous exponential growth model, find the growth rate. Well, continuous exponential growth, that is a model that looks like this. Okay, where we'll just say P is equal to e to the RT, and let's put in an initial value here. Okay, and let's change this to A of t. Okay, so my amount, or in this case, price share at a particular year t, is equal to the beginning stock price times e to the RT. And our job here is to find the growth rate, that value right there. So how do we set this up? Well, what they're doing is they're telling us what the share price was 4 years after January 12th. So that's going to be the value A of t. So we're going to put in here 3.85. That was our stock price, but it started at 72 cents per share. So that would be our A0, our value of the share at time t equals 0. And then that would be equal to e raised to the r, and t is 4 because we're talking about this price being 385 4 years after 2012. And so we're going to solve this for r. So this is an exponential function. So we're going to, first of all, isolate our exponential portion by dividing by 0.72. So I will get out the TI-84 and we'll do this. And I'm going to take $3.85 and divide that by 0.72. That's going to give me 5.3472 is equal to e to the 4r. And what I'm going to do is I'm going to use natural logs. I'm going to take the natural log on both sides. I'm going to have the natural log of 5.3472 is equal to the natural log of e to the 4r. The natural log is log base e, right? So log base e of e to the 4r is just 4r. It releases the exponent and just gives me 4r, right? These guys cancel each other out. And that's natural log of 5.3472. And so our rate, if we assume that this growth in the stock price was exponential and it fit a continuous exponential growth model, it would be the natural log of 5.3472 divided by 4. So on my TI-84, I'm going to do natural log of this number and then divide that by 4. And there you go. So this looks like the growth rate 0.419. So approximately a 42% growth rate is our answer to that using logarithms. Well, class, I hope that was helpful to you as a review of logs and exponentials and how we use their inverse properties to solve either log equations or exponential equations. And that is it. So I will be having another live stream next Sunday as well to cover another topic on to help you get ready for Calc AB. Don't know exactly what that is, but I'll put out the announcement here on YouTube fairly shortly in the next couple of days so that you know, and hope to see you here next Sunday. Thanks for tuning in. I sure appreciate it. And I will see you next time around, either this coming Thursday or next Sunday. Bye, everybody.